Alright, so how exactly is this true? I'll show you exactly how using a little bit of geometry. Alright, so we have this setup over here, and it's a linear function where we have a point A and B expressed as vectors, and we have the corresponding outputs f of A and f of B. Now, we'll define D is equal to B minus A, which is that purple vector right there in the diagram. And the diff of D we will define as f of B minus f of A. So that is the difference between these outputs. So that is equal to mb plus c minus ma plus c, because this is a linear function. You know, y is equal to mx plus b. That's what I'm using there. That's equal to m times b minus a, which is equal to m times d. Now we have the diff of, if you scale the input d, then the diff of, cd, oh, whoops, whoops, I meant to say the diff of ed, actually, is equal to med, which is equal to emd, which is equal to e times the diff of d. So that means that if we scale the input vector, then we scale the output difference by the same factor. And this is important to remember in the next slide. All right, so we have a setup here, and this is the domain. As h approaches 0, we get linear functions between these 3 points specified here by those gray spheres. So we have f prime of p naught plus qk is equal to the limit as, that limit right there as h approaches 0, as you could see in the diagram. Then we get that stuff. We could actually decompose this into the, if you think of the, how do I say this? Oh yeah, you could just decompose it like that. And remember from the previous slide, for linear functions, scaling the input between 2 points in the domain scales the difference between the two corresponding outputs by the same factor. So since we have hqx and hqy, we're actually scaling the partial derivatives by qx and qy. So we get this right there. And we're actually evaluating these partial derivatives of p, which is just some, some dummy vector. We're actually evaluating them at the specified points right there, as you can see in the diagram. So we have this over here. It's actually equal to that. Then we have, we can actually replace that limit as h approaches 0 of hq x bar, x hat, with a 0, because as h approaches 0, that term right there approaches 0 too. And then we could think of this in terms of the dot product of these two vectors. And we could think of that as the vector q, the vector q dotted with the gradients of f of p, where p is a dummy vector, evaluated at p is equal to p naught plus qk. Right there. And so we get that right there. Because we're evaluating at k is equal to 0, we're going to get the dot product between the q and gradient vectors evaluated at p is equal to p naught, which is the equivalent